Hello everyone, we were looking at the estimation of hydraulic conductivity function by multi-step outflow technique. We have also discussed the limitations of the technique and as well as the usefulness of the technique. The technique is useful for the estimation of both soil water characteristic curve and hydraulic conductivity function to maximum suction value of 1500 kilopascal if we use 15 bar higher entry porous disc. There are other various techniques people often use on and off, such as steady state flow techniques. So we often use steady state flows and transient flows through saturated porous media for the estimation of saturated hydraulic conductivity. Similar techniques are also used in the literature for the estimation of unsaturated hydraulic conductivity at various suction values by controlling the suction. So you may have a soil column. It is connected to two different reservoirs. So now here we maintain certain head and we allow the water to take place, go through it. However, in unsaturated hydraulic conductivity technique, the airflow is also considered and higher entry porous discs are used at the top and bottom of the soil column. And here also, similar to the access translation technique or multi-step outflow technique, the air pressure is controlled and water pressure is certain value of water pressure is maintained, and the suction is controlled in the soil, and under this controlled suction the flow is allowed to take place. Such techniques, we understand that such techniques are applicable for coarse grained soils. So in that in coarse grained soils it is easy to control the air pressure and maintain the water flow to take place through the soil. Otherwise, if it is a clay soil, we will not get appreciable amount of water through the soils at the outlet. Similarly, often centrifuge techniques are also used, where you have a soil sample placed in the centrifuge and which is rotated at certain angular velocity. So when it is rotated, a centrifugal force is applied on the soil mass. So then the water flow will be faster, because compared to the saturated flows, unsaturated flow through unsaturated soils, the flow rate will be very less. So here in the centrifuge, the flow rates can be improved or increasing the acceleration. So such tests are also often used in the literature. However, such techniques are also applicable for coarse grained soils, because in fine grained soils, soil will start settling and consolidation takes place. Therefore, such techniques are limited for coarse grained soils only. So therefore, hydraulic conductivity function estimation for all soils may not be possible, and even for coarse grained soils, the determination in the laboratory is very expensive. So therefore, often the hydraulic conductivity is determined from the soil water characteristic curve itself. Once the soil water characteristic curve is properly determined in the laboratory by using different techniques, using different ways that we will discuss very soon, the HCFs can be predicted. So such prediction models are very commonly used in the flow through unsaturated soils. Let us look into several SWCC and HCF models available. We also require to model the soil water characteristic curve data. So that is when we get volumetric water content versus suction, or so the theta versus psi, or gravimetric water content versus psi, or degree of saturation versus psi. This data when we obtain in the laboratory, such as these data points, we need to obtain a smooth curve such as this curve for the modeling purpose, because the soil water characteristic curve and hydraulic conductivity function are required input data for the flow through unsaturated soils. So therefore we require a smooth functional form between psi and theta and k versus psi. So these functions are often required for the hydraulic conductivity for the flow through unsaturated soils. So therefore we require to model the measured data from the laboratory or in the field. So we have several SWCC models available in the literature of unsaturated soil mechanics, such as Brooks-Corey model, which is proposed in 1964. So this is theta is equals to theta s when psi is less than or equal to psi b. Psi b is the bubbling pressure. So this is bubbling pressure, which is nothing but the air entry value, the air entry suction. So when it is air entry suction or less than air entry suction, theta is equals to theta s. When the suction crosses bubbling pressure, then you have theta r plus theta s minus theta r times psi b by psi power lambda. Here lambda is a pore size distribution factor and psi b is the bubbling pressure or air entry value. So in this equation the lambda values generally vary between 0 point small values, maybe 0.1 or something, and it can go up to very large values like 2 or so. Larger values of lambda signifies uniform pore size distribution and smaller values of lambda signifies the well gradation. So therefore this equation also can be written as, the bottom one can be written as theta minus theta r by theta s minus theta r is equals to psi b by psi power lambda. So which is nothing but, which is referred with a bigger theta, which is called a normalized volumetric water content. So here theta r is the residual water content, residual volumetric water content, and theta s is the saturated volumetric water content. So therefore when we plot a big theta, that is normalized volumetric water content, and on x axis you have psi suction, then for different values of air entry value, and for another air entry so this is how it varies. The normalized volumetric water content varies from 0 to 1 because when the theta approaches saturated value, saturated volumetric water content, that is equals to porosity, then this whole thing becomes 1. So there is 1. So as when the bubbling pressure is, when the suction is less than or equal to the air entry value or the bubbling pressure, so theta is equals to theta s, therefore that is equals to 1, and if psi or suction is more than the bubbling pressure, then the normalized volumetric water content decreases from 1. So this is how it varies. These three are for different air entry values, for different AEVs. Similarly, for different lambda values, the normalized volumetric water content versus psi varies in this manner. The AEV remains same, so this is how it varies. So AEV remains same, but lambda values are different. This may be for lambda equals to 0.5 and this may be lambda equals to, this is for lambda equals to 2. So lambda equals to 2 or very large values indicate uniform pore size distribution. When you have uniform pore size distribution, you have a steep soil water characteristic curve, and the residual water content is achieved at very small value of suction, because all the pores are uniform. So water retention is not that significant because it immediately loses its water as the suction increases. On the other hand, when you have well graded soil, you have several different types of pores, you will generally have smaller pores in that particular case. So therefore it extends, the residual water content is expected to be existing at very high values of suction. So therefore the slope is not steep and it extends to very large values of suction. So this can be simulated very well using this particular expression given by Brooks and Corey, and which is very simplest possible model because it has only one parameter to estimate. So only lambda needs to be estimated while fitting the data. So the bubbling pressure can be usually when you plot in terms of normalized volumetric water content and suction, generally the bubbling pressure can be identified or observed, generally that is known. So therefore only one fitting parameter is available. Often we may not know the residual water content value, and therefore in that particular case the two parameters need to be estimated from the data. So this is very simple technique, that is the advantage of this particular model. However, the major disadvantage is that the discontinuity at air entry value, which has a discontinuity which is 1 up to the air entry value, and beyond that it decreases. Here there is a discontinuity. If you take the slope d theta by d psi, d theta by d psi, then this value is not defined at this particular point. So therefore you cannot obtain a smooth function using Brooks-Corey method. And we have another method called Van Genuchten model, which is very popular for the estimation of soil water characteristic curve from the measured data of theta versus psi. So the expression is theta is equals to theta r residual water content plus theta s minus theta r, similar to the Brooks-Corey model, times 1 over 1 plus alpha h whole power n. So here n should be more than 1. So here this mod indicates the h should be positive value should be substituted here, or alpha h should be positive, and because the expression is in terms of matrix suction head, and matrix suction head is negative value, so you will get complex numbers if n is real number. So this is normalized volumetric water content is equals to 1 by 1 plus alpha. Often this is written as psi by a whole power n, and this whole power m. Often this is written in this particular form in our geotechnical engineering. This initial expression was available in the soil science literature. When it is used in geotechnical engineering, we are acquainted, or we often use a soil water potential or suction directly. Therefore the expression is modified into this. Here a represents air entry value, which is 1 over alpha when you compare with this expression, and a is related to air entry value, but it is not equal to the air entry value. So therefore this is also a fitting parameter. Often it is shown on several soils and using the modeling also that a is not equal to the air entry value, which is related to air entry value. When you have a large air inter value and the A value is higher, when you have a smaller air inter value for a given soil, A is small. So qualitatively these two can be related, however they are not quantitatively equal. So the other parameters are M and N. So N is related to the pore size distribution of the soil. M controls overall symmetry of the soil water characteristic curve. So when theta r is also not known, then you have 4 parameters to estimate or determine. So we will see how generally these parameters are determined from the laboratory estimated data of theta versus psi. Theta s generally known because when you conduct a test, initially at slurry state or whatever the state the soil is in, at fully saturated state the porosity of the soil is known. Knowing the density of the soil and water content, one can estimate the dry density of the soil. From that one can estimate the void ratio. When void ratio is known, that is, it can be related to the porosity, and porosity at fully saturated state is the volumetric water content at saturated or saturated volumetric water content. So that's how one can estimate the theta s in the tests. However, theta r estimation is little difficult, and sometimes you can use theta r is equals to as small as possible for clays, say 0.01 or something like that. People often use. And here the n value should always be more than 1. So this is the constraint coming from the equation. So let us try to understand why n should be more than 1. If I write in terms of alpha h only and h is used in positive terms, then this is the expression that I can derive. So the normalized volumetric water content can be written as 1 plus alpha h power n whole power minus m. When you differentiate this expression, dH, which is minus m times 1 plus alpha h whole power n power minus m minus 1, therefore I can write it as minus m plus 1 and times n alpha h power n minus 1 times alpha, which can be written as minus alpha m n minus alpha m n times 1 plus alpha h power n whole power minus m plus 1 times alpha h power n minus 1. If you see this expression, as h approaches 0 and if you consider n value to be equals to 1, so this slope d theta by dh would approach minus infinity. So the slope of the soil water characteristic curve, if this is a soil water characteristic curve, if this is a soil water characteristic curve, at this point where h is very close to 0, so the slope of the equation is approaches minus infinity. So that means this will never go to 0, but it approaches to minus infinity. So because of which what will happen is the diffusivity is defined as k times dH by d theta approaches 0. So which is not physically correct. The diffusivity becomes 0 as k approaches ks which approaches Ks, which is not equal to 0. So therefore diffusivity should become 0. So this happens because when you consider n equals to 1, and similarly when n equals to less than 1 also, at when h approaches 0, so this whole expression approaches minus infinity. So therefore diffusivity approaches 0. If n is greater than 1, then this whole expression is well defined. Therefore generally the n is restricted to be more than 1 in this particular model. So Van Genuchten model is very well received, and the work by Van Genuchten at 1980, so this particular work or journal paper received more than 20,000 Google Scholar citations. So this work is very well received, and even till date the Van Genuchten model is widely used for representing the soil water characteristic data, and often used for in the modeling of unsaturated flows. The major advantage of Van Genuchten model when compared with Brooks-Corey model is it can provide a smooth SWCC curve. So there is no it's a very smooth function, or there is no discontinuity anywhere. However, the drawback with Van Genuchten model is that so the volumetric water content can never goes to 0 at any given suction. If you look at the theta versus psi, this decreases, and because of the nature of the equation, the asymptote, this will never approach to 0. So this is a major issue using Van Genuchten model. All these models are very simple. One can generate different curves by varying the model parameters like A, M, N. You can assume some values for these parameters, and one can play with this on spreadsheet, and you will understand how each parameter influences the nature of the SWCC curve. So you would see that this would never becomes 0, it only approaches 0 at any given suction value, which is physically not correct, because thermodynamic point of view, this has been observed that when suction value is at 10 power 6 kilopascal, that is 1000 megapascal, the water content should become 0. However, in Van Genuchten model that doesn't happen. So there is another popular model proposed by Fredlund along with his co-investigator Xing, proposed another SWCC model in 1994. In this model the expression is theta equals to 1 minus log 1 plus psi by psi r divided by log 1 plus 10 power 6 by psi r times theta s divided by log e, that is exponential of 1, plus psi by a whole power n whole power m. So this is kind of similar to your Van Genuchten equation. However, you have log here and exponential form here, exp of 1 here, and you have one coefficient or variable here before this one. Here psi r is the suction corresponding to residual water content, and in Fredlund and Xing they often mention that theta r determination is also difficult, therefore that also adds up as one of the fitting variable. So however, in Fredlund and Xing model you have another fitting variable, that is psi r, suction corresponding to water content. This value is often modeled along with other fitting parameters like a, n and m, or psi r is substituted with 1500 kilopascal in some of the Fredlund's works. In some works psi r is considered to be 3000 kilopascal also. So in some papers psi r is also used as a variable, and which is also fitted along with other parameters. So psi r you can also assume which is equals to 1500 kilopascal, and such fixing of psi r value is done often in some of the models like GeoStudio, etc. So in this particular model, interesting part is that here you have 10 power 6 value, therefore all psi values should be substituted in kilopascal, and this 10 power 6 kilopascal value indicates that at psi is equals to 10 power 6 kilopascal, when it is plotted theta versus psi, (10 power 6 kilopascal), this curve is forced, or the water content is forced to come to 0. So when you substitute psi equals to 10 power 6 kilopascal, that is at suction equals to 10 power 6 kilopascal, so this value becomes 1, so 1 minus 1 is 0, so theta is forced to come to 0 at theoretical value of at 10 power 6 kilopascal, 1000 megapascals. So therefore based on the theoretical observation or thermodynamic point of view, they observed that at 10 power 6 kilopascal the water content should go to 0. Therefore based on that they modified the Van Genuchten model to bring in that feature that the water content goes to 0 at 10 power 6 kilopascal. So even though the model parameters here n, m and a, n, m are often understood to be flexible, the restriction we made on Van Genuchten equation and Van Genuchten model, like n greater than 1, may be applicable in this particular case also. So the advantage is here also you can generate a smooth SWCC similar to Van Genuchten equation, and extra advantage may be that the water content is forced to 0 at very high suction values. Therefore for clay soils where the suction range extends to such values, because for clay soils the suction range extends to 10 power 6 kilopascal. However, there is a major disadvantage also often observed by our group, in fact, that because of this particular feature, often it is seen that when theta versus psi is plotted, the plots often go, and then because it has to go to 0 here, often bimodal curves are obtained using Fredlund and Xing model. So this is the soil water characteristic curve is the which decreases, and after that which is forced to, when you plot this, for often this is seen that which value decreases because it has to approach, it should have gone, the curve should have approached directly here, but instead of that, because it has to go to 0 at 10 power 6 kilopascal, often the curve behaves in a different manner, and often bimodal curves are obtained using Fredlund and Xing model, often like this, or sometimes it is like this. Such bimodal behavior is observed, which does not have any significance. However, because of the model restriction that theta should go to 0 at psi equals to 10 power 6 kilopascal, such discrepancy is observed in the models. We have several other models like Campbell model, where theta is equals to theta r plus theta s minus theta r times 1 plus psi by psi naught into exponential of minus psi by psi naught. Here psi naught is the soil water potential at the inflection point on the curve. Theta r is residual water content and theta s is saturated water content. And the Gardner's expression, the gravimetric water content is equals to the saturated water content divided by 1 plus a times psi power n. Here a and n are fitting parameters. Similarly, Broadsword model where psi is equals to A times Ws by W minus 1 whole power 1 by n. Here A and n are fitting parameters or model parameters, and others are similar to here. And Mackey and Bum model, psi is equals to A minus n log of W by Ws. Here again A and n are fitting parameters, and W is water content at any given suction, and Ws is saturated water content. So not just these models, we have several tens of models that are available in the literature and often used, but most often used models are only the three which are discussed little elaborately, that is Brooks-Corey, Genuchten and Fredlund and Xing. We have seen that the Brooks-Corey model has a discontinuity at the bubbling pressure or the AEV or air entry value. Therefore, even though it is very simple, often in the modeling of partly saturated flows, it is very difficult to use. When it comes to the Genuchten model, which is a 3-parameter model which can generate smooth soil water characteristic curve. However, the water content only approaches to 0, but it doesn't become 0 even at a very high suction values. When it comes to the Fredlund model, Fredlund and Xing model, the feature, it has a feature for reducing the volumetric water content to 0 at suction value equals to 10 power 6 kilopascals. And this has a new model parameter such as a psi r, psi suffix r, which is a suction corresponding to residual water content, which needs to be either determined along with the other fitting parameters such as A, M and N, or which can be fixed to certain value like 1500 kilopascal or 3000 kilopascal. Another important point here with Fredlund and Xing model is, our limitation is that this cannot be reversed, or it cannot be written as psi in terms of theta. Genuchten model can be reversed, or inverse form can be written, but Fredlund and Xing model cannot be written as psi of theta. That is a major limitation. So therefore, with other hydraulic conductivity models, this integration is a little difficult. That we will see now. When it comes to the hydraulic conductivity function models, as I explained that not many experimental techniques are available for the determination of hydraulic conductivity function in the laboratory as well as field. Only the multi-step outflow technique is available. That too, it has a limitation to use more than 1500 kilopascal. So this is mostly restricted for coarse grained soils. So hydraulic conductivity function is often determined from the soil water characteristic curve data only. So for that, we need to understand what different models we have. In hydraulic conductivity function, we have empirical models, macroscopic models and statistical models. The empirical and macroscopic models, these are simple functions. They may use Ks in the expression and some curve fitting parameters. These are simple expressions like y equal to mx plus b, such as linear expressions or something like that they use for the hydraulic conductivity functions. And or using the macroscopic behavior, they may see the similarity between HCF and SWCC. Based on that, they utilize similarity between these parameters and they use to predict. Generally, the empirical models and macroscopic models are fitting models for the existing hydraulic conductivity function data. When you have determined using pressure plate apparatus the hydraulic conductivity data, then these models can be used to fit and determine the fitting parameters. On the other hand, the statistical models are advantageous because there is a theory behind it. So the hydraulic conductivity of they assume. So in the statistical models, if you assume that this is one cross section where this is one point where you have several pores that are available, so in between you have soil grains. So in such scenario, so this is one, for example, you have several soil particles which are placed in this particular manner, there is no overlap. So this is a one particular soil structure. When I consider the cross section at any given place, the cross section is this. You have several pores designated by say R1, R2, R3, which are distributed. Here we consider circular pores that exist, and then we consider the probability of connecting one soil pore with the adjoining water filled pore with some probability, and then we can consider that if there is a probability that this pore exists in the next to the other pore in the next cross section, what is the probability of that? Because if there is a probability that there is a pore exists, then flow takes place through that using Hagen-Poiseuille's equation. So the which states that the hydraulic conductivity is a function of R square, and as we know, if you consider circular pores, R can be approximated as 2 Ts by H times gamma W, because this pressure is equals to 2 Ts by R. So when we assume that the contact angle is 0, so therefore hydraulic conductivity is function of 1 over H square, or the head, suction head. So this is how the function is related. When different probability functions are used, you may get expression like K equals to Ts square by 2 mu rho Wg times epsilon square by n square times 1 over H1 square plus 3 by H2 square plus 5 by H3 square, like that, and 2n minus 1 by Hn square. So such expressions would result for hydraulic conductivity of unsaturated soils. Here Ts is surface tension, mu is viscosity, rho Wg, and epsilon is the dielectric, and n is porosity. So here the different expression for hydraulic conductivity function based on statistical models will have K as a function of 1 over H1 square plus 3 by H square to H2 square, like that you will have. So essentially they indicate different pores sizes you have in the soil mass. So if you look at different available models, so the old one is Richard's model, which is as old as 1931. So the model is a linear assumption. The hydraulic conductivity is inversely linearly dependent. So simple linear equation where A psi plus B, which is used. This is a simple empirical equation, and Gardner here 1958 had a given expression which is Ks, which uses saturated hydraulic conductivity. So Ks by 1 plus A times psi n. A and n are empirical parameters. So whenever you have these empirical equations, the fitting parameters need to be determined. These are fitting parameters. The fitting parameters need to be determined by considering best fit between the measured hydraulic conductivity data and the expressions. And the Brooks-Corey method, which is a macroscopic model, because which considers similarity between soil water characteristic curve and hydraulic conductivity function, and based on the similarity where you have lambda which is related to n. So that is how it is used, and so this is a macroscopic model. Similarly, Campbell proposed another model which is also a macroscopic model. So these three are statistical models. You have many other statistical models, but here I have given three such models. This is based on Hagen-Poiseuille's expressions, where Jackson model, where it considers k of theta I is equals to saturated hydraulic conductivity times theta I divided by theta S. So theta I is at any given point I value, and theta I by theta S times sigma j equals to 1 to m 2j plus 1 minus 2i times hj power minus 2, that means 1 over h square. That is how we have used also using Hagen-Poiseuille's approximation. This form is divided by sigma j equals to 1 to m 2j minus 1 divided by h square. So this form is derived based on Childs and George expression, and here k is the hydraulic conductivity at any given theta. Fine. So this is another model which is a Budin model, and here the expression is in terms of relative hydraulic conductivity, where relative hydraulic conductivity is hydraulic conductivity at any given water content divided by the saturated hydraulic conductivity, k by ks, which is equals to theta square times integral 0 to theta, this is a normalized volumetric water content, 1 by h square x dx by 0 to 1 by h square x dx. Here x is integration variable. The Moolam expression is also similar to Burden model. So these two expressions, Moolam and Burden are very often used in the geotechnical engineering as well as in soil science literature also. Here, for integrating or for estimating the hydraulic conductivity function from the soil water characteristic curve data, we require a continuous function of h of theta. Here if you have h of theta, so we can directly substitute it here and we get an expression for hydraulic conductivity function. So here we do not require any other fitting parameters. Whatever the fitting parameters we established for the soil water characteristic curve can be directly used for the hydraulic conductivity function determination. This is also seen for many coarse grained soils. These models provide very satisfactory results. Here if you see the Genuchten model, if you recollect your Genuchten model, so that is theta is equals to 1 by 1 plus alpha h power n and whole power m. So here it is written theta equals to function of h, but this also can be written h as a function of or another function of theta. So inverse is very easy to do, because that is what is required for the estimation of hydraulic conductivity functions here. However, if I go back using Fredlund and Xing model, in this expression it is not possible to represent psi as a function of theta, because inverse is not possible. So that is a major limitation of Fredlund and Xing model. So that is the reason why they use a different expression for determination of hydraulic conductivity function, which is called Kunz model. Kr theta r to theta, theta minus x by psi square x dx divided by theta r to theta s minus x by psi square x dx. So this is the expression used Fredlund to combine with Fredlund Xing SWCC model for the prediction of relative hydraulic conductivity. So let us see one of such derivation for hydraulic conductivity function determination using SWCC, where the Van Genuchten model is combined with Moulomb expression, then you get analytical expression for hydraulic conductivity functions. So once the SWCC parameters are available, directly we substitute these parameters to obtain the hydraulic conductivity function. As we have seen, the theta is equals to 1 by 1 plus alpha h over n whole power m, which can be written as in terms of h as h is equals to the theta power minus 1 by m, and if you take the minus 1 that side, minus 1, then whole power 1 by n and 1 by alpha. Such a simple thing to invert the expression. So here Van Genuchten and Moulomb model, this is the model for hydraulic conductivity function estimation, and we can derive analytical solutions for hydraulic conductivity function by combining the SWCC model and the expressions given for hydraulic conductivity functions. One of such integration between SWCC and hydraulic conductivity function is Van Genuchten model. So in this model, the Van Genuchten model we have earlier written, which is theta is equals to 1 by, theta is big theta, which is normalized volumetric water content, which is equals to 1 by 1 plus alpha h. Here h should be substituted in positive thing, power n whole power m, which can be inverted to write expression for h as theta power minus 1 by m, and then minus 1 goes to the other side, and whole power 1 by n, and alpha, if this comes this side, 1 by alpha. So such a simple expression can be derived because inversion is so easy. So when we invert the expression, we get the h in terms of theta as this. Now the Moulomb model is Kr, the relative hydraulic conductivity, is equals to big theta power half into integral 0 to theta 1 by h of x dx by 0 to 1 by h of x dx whole square. So h can be substituted here to obtain the expression for Kr. So therefore directly when alpha, m and n are determined by fitting the soil water characteristic or data using this model, so that directly the parameters can be substituted here to obtain the Kr, relative hydraulic conductivity. So here when we substitute, this is theta power half, and so this becomes 1 by alpha get cancelled because that coefficient is present on the numerator and denominator as well, so that get cancelled. So when you write this expression as 1 by theta power m, 1 by m, so then this can be written as theta, and using the integral variable, that is x, this can be written as x power 1 by m by 1 minus x power 1 by m divided by integral 0 to theta dx and integral 0 to 1. This is the same expression, x by 1 by m, x power 1 by m divided by 1 minus x power 1 by m dx So this can be simply written as theta power half, this is f of theta by f of 1, because it is the same expression, but the integration is here going from 0 to theta and the integration here going from 0 to 1, that is the only difference. So if you obtain f value, then you can obtain f of 1 value also. You can obtain f of theta value, then you can obtain f of 1 value also. So the f of theta value is integral 0 to theta x power 1 by m by 1 minus x power 1 by m dx. This can be simplified by substituting x power 1 by m is equals to y. If we do that, dx is equals to m y power m minus 1 dy. Substituted, then this expression becomes f of theta is equals to integral 0 to theta y power y times y by 1 minus y, and for dx this is m times y power m minus 1 dy. No, here this whole power n, sorry, I forgot to put the whole power n 1 by n. So in the expression, so therefore this is whole power 1 by n. So this can be written as m times 0 to theta y power 1 by n plus m minus 1 into 1 minus y power minus 1 by n dy. Here also the phi is phi power 1 by m should be substituted, theta power 1 by m should be substituted. So here also the integration variable changes from 0 to theta power 1 by m, because we are substituting this value, it goes from 0 to y. So here this is theta power 1 by m. So this is the change. So then we get an expression for phi of theta, which is m times integral 0 to theta power 1 by m y power m minus 1 plus 1 by n into 1 minus y power minus 1 by n dy. This is a particular form of incomplete beta function. In its initially, the Genuchten thought in 1980 that in its most general form this equation does not have any analytical solution. So therefore he started deriving particular solutions. He assumed that for example, when you assume m minus 1 plus 1 by n is equal to some value, say k, then you can derive particular solutions by assuming k equals to 0, k equals to 1. Likewise, you can derive any number of particular solutions. So for example, k equals to 0 results in one particular solution, that is f of theta is equals to m times 0 to theta power 1 by m 1 minus. So as we have seen, the function f of uppercase theta is equals to m times integral 0 to uppercase theta power 1 by m y power m minus 1 plus 1 by n times 1 minus y power minus 1 by n dy. So, this is a particular solution of incomplete beta function, and Genuchten in 1980 felt that this particular form does not have an analytical solution. So, therefore, he derived particular solutions for this particular equation. So, to derive particular solutions, he assumes m minus 1 plus 1 by n is equals to k, and one particular solution when k is equals to 0 is, when k equals to 0, this is m equals to 1 minus 1 by n. So, substituting k equals to 0 into the above equation results in f of uppercase theta is equals to m times this m minus 1 plus 1 by n is 0, therefore, y power 0 is 1. So, this results in m times integral 0 to theta uppercase theta power 1 by m times 1 minus y power minus 1 by n dy. So, when we integrate this, m times the integration for this is minus 1 minus y 1 minus y. So, this is for inside, and for this here we can substitute instead of n, we substitute instead of 1 minus n m minus 1 here. So, because all the parameters are with in terms of m. So, when we substitute and do the integration, this is simply 1 minus y power m divided by m. The integration is, the limits are from 0 to uppercase theta power 1 by m. This m gets cancelled, and this is nothing but minus 1 minus uppercase theta power 1 by m power m, and minus, when the 0 is substituted, this is again minus 1. So, therefore, this is 1 minus uppercase theta power 1 by m whole power m. So, this is f of uppercase theta. Now, f of 1 is simply the same thing, that is from here minus 1 minus y power m power, the limits are 0 to 1. So, when you substitute, this is 0, then minus, when you substitute the 0, this is minus 1. So, minus of minus 1, this is 1. So, therefore, the Kr relative hydraulic conductivity as a function of uppercase theta is equals to f of uppercase theta by f of 1 times uppercase theta power half times 1 minus uppercase theta power 1 by m power m, this whole square, because Kr of uppercase theta is equals to uppercase theta power half times f of uppercase theta by f of 1 whole square. This is from Moulomb's model, therefore, this is the solution. But however, there is a condition that m should be equals to 1 minus 1 by n, and m should be between 0 and 1. So, these are the conditions for this particular form of equation. Similarly, we can derive for Burdin's model, and similarly another particular solution also can be derived when for k equals to 1. So, this becomes m plus 1 by n minus 1 is equals to 1, that means m is equals to 2 minus 1 by n. So, when m equals to 2 minus 1 by n is substituted, so f of big theta or f of uppercase theta is equals to m times integral 0 to uppercase theta power 1 by m, and 1 minus y power, it should be m minus 1 plus 1 by n. So, this became 1 times 1 minus y power minus 1 by n. For minus 1 by n we can substitute m minus 2 dy. So, when this is solved using integration by parts, we obtain a solution for kr of uppercase theta is equals to theta power half times 1 minus m times 1 minus uppercase theta power 1 by m power m minus 1 plus m minus 1 times 1 minus uppercase theta power 1 by m power m whole square. So, this is the expression for relative hydraulic conductivity in terms of uppercase theta, or that is normalized volumetric water content. Here the condition is that m should be equals to 2 minus 1 by n. So, this is another particular equation. So, earlier we derived one particular equation by assuming k equals to 0, and this is another particular equation by assuming k equals to 1. Similarly, n number of particular equations can be developed by assuming different values for k. Similarly, using Burdin's model, that is a Genuchten Burdin's model. So, using the Burdin's model, gives that kr of uppercase theta is equals to uppercase theta square times integral 0 to uppercase theta dx by h square x divided by integral 0 to 1 dx by h square x. So, by inverting Genuchten equation, the Genuchten equation is big theta is equals to 1 by 1 plus alpha h power n whole power m. When you invert this expression to write h equals to h of theta, so this gives theta power 1 by m when you take the m other side, and when you put minus 1 by m, this is simply 1 plus alpha h power n, this equals to. So, therefore, minus 1 you can bring the 1 on the other side, so this becomes minus 1. So, then if you take n the other side, 1 by n and divide by 1 by alpha is h. So, then if you substitute for h here, then kr of uppercase theta is equals to uppercase theta square times, this is 0 to uppercase theta. So, this is dx by h square. Anyways, you have the same expression on the numerator and denominator, the alpha gets cancelled. So, then this can be written as h is 1 by alpha, this can be written as 1 minus big theta power 1 by m by big theta power 1 by m. So, this is 1 by h here. So, this one can be written as 1 minus x power 1 by m whole square, or dx, I will write it separately here, and this one is x power 1 by m. So, this whole thing need to be squared. Here there is 1 by n. So, there is a 1 by n term and square. So, this is 2 by n. Similarly, this is 0 to 1, 0 to 1, x power 1 by m divided by 1 minus x power 1 by m whole power 2 by n dx. So, this is expression to solve. This can be written as big theta square times f of theta by f of 1, because the functional form is same except that the limits are different. So, this is written in this manner. So, now let us solve f of big theta. This is equals to integral 0 to theta x power 1 by m by 1 minus x power m by m whole power 2 by n dx. Similar to the earlier Van Genuchten-Moolam equation, we again substitute x power 1 by m is equals to y, or this can be written as x equals to y power m, then dx is equals to m y power m minus 1 times dy. So, this is the expression for dx, and here the functional form can be written as 0 to, here when this is earlier when you have x, this is 0 to x, now this is y power m. So, x is substituted to y power m. So, this is y power 1 by m times here x power 1 by m is y power 2 by n times 1 minus y power minus 2 by n, and instead of dx if you substitute m y power m minus 1 dy, then the integration for this can be obtained by simplifying 0 to theta power 1 by m. This is y power these two terms together m minus 1 plus 2 by n times 1 minus y power minus 2 by n dy. Again, this is a general expression and this is an incomplete beta function. So, Van Genuchten felt that there is no analytical solution. So, he derives particular solutions by assuming again minus 1 m minus 1 plus 2 by n is equals to k. One particular solution when k equals to 0 is f of theta is equals to m times 0 to theta power 1 by m. So, this is 1 minus y power minus 2 by n dy. Here minus 2 by n, this is equals to 0. So, m minus 1 is equals to minus 2 by n. So, here this can be written in terms of m 0 to theta power 1 by m 1 minus y power m minus 1 dy. So, the integration is m times. So, for 1 minus y power m minus 1, the integration is minus 1 minus y power m divided by m. The limits are from 0 to uppercase theta power 1 by m. So, m gets cancelled, and when you apply the limits, this is 1 minus uppercase theta power 1 by m power m. So, this is f of uppercase theta f of 1 is equals to minus of 1 minus y power m from 0 to 1. So, when 1 is substituted, this is 0, and minus, when 0 is substituted, this is minus 1, minus of minus 1, this is 1. So, when this is simplified, when this is kr term is written, kr of, so when kr is written, kr of theta is equals to theta square times f of theta by f of 1. So, this is equals to uppercase theta square times 1 minus uppercase theta power 1 by m whole power m. So, this is kr of theta. So, this is the analytical solution, particular form of analytical solution for Budin model, Van Genuchten Budin model. Here m is equals to 1 minus 2 by n, and m varies between 0 and 1, and n is more than 2. So, these are the conditions. This is another particular form of VG Budin model. Similarly, when k equals to 1, k equals to 2, by substituting several integers for k, we get infinite number of particular solutions of the general form using Van Genuchten Budin, similarly Van Genuchten Moolam. However, in 1985, after 5 years from this work by Van Genuchten, he realized that the general form of the equation that is derived has analytical solution. So, then he published a work along with Nielsen in 1985, where he provides general analytical solution for these equations. So, for the Van Genuchten Moolam, so the expression is f of uppercase theta is equals to m times integral 0 to uppercase theta power 1 by m y power m minus 1 plus 1 by n times 1 minus y power minus 1 by n dy. So, here we assumed m minus 1 plus 1 by n is equals to either 0, 1, etc., and then we derived analytical solution, but this general form can be expressed as m times incomplete beta function and some zeta parameter of pq and complete beta function b times pq. This can be expressed in this particular form, and the incomplete beta function and beta function values can be obtained table form that was available during that time, and then using that they got the analytical solution. And now in MATLAB and many other programs, the incomplete beta function and beta function values can be readily obtained, and this can be solved easily. Here the zeta parameter is 5 power 1 by m, and here the p is m plus 1 by n, and the q is 1 minus 1 by n. So, therefore, the kr of uppercase theta is equals to, because f of 1 is m times complete beta function pq. So, therefore, k of theta is equals to square root of uppercase theta times incomplete beta function whole square. So, this is the general solution. Similarly, using Van Genuchten burden, using the same reference Van Genuchten and Nielsen 1985. So, the general expression can be written as Kr of cap uppercase theta is equal to uppercase theta square, the incomplete beta function of Rs. Here this zeta is same, uppercase theta power 1 by m. Here R is equals to m plus 2 by n and S is equals to 1 minus 2 by n. So, here there is no restriction between m and n. So, there is no, these are not constrained parameters. Earlier, whatever the solutions we derived, those are particular solutions where m is related to n. Here m and n are not related, m and n are independent in these two expressions. So, these are general expressions. As can be seen, now you have general solutions for Van Genuchten and Moulomb, Van Genuchten and burden. Similarly, you have particular solutions by assuming k equals to 0, 1, 2 and different values. Even though these many number of solutions are available, most commonly m and n are dependent equations are only commonly used for fitting SWCC data. So, this is probably because one reason is that this particular work is not cited that well, or there could be another reason is that when m and n are independent, so the equations overfit the SWCC data and the hydraulic conductivity functions when they are estimated, they deviate significantly from the measured data. However, when the m and n are restricted, even though the error between SWCC data and theoretical data is slightly more than the m and independent case, but the hydraulic conductivity functions are very close to the measured data. So, that is the reason why m and n dependent conditions. So, those are the particular solutions which we derived earlier. So, these particular solutions are commonly used instead of general solutions. Thank you.